right, good afternoon, good evening, good morning, whenever you happen to be watching this. Hello, let's see, I'm obviously not recording this at the normal time. The normal time for this class is on Tuesday and Thursday afternoon, but because I'll be out this week for the Thursday, I'm holding a makeup session or an online session for ENGR 2302 Engineering Dynamics. So this will be the sixth lecture in the series of ENGR 2302 Engineering Dynamics. And here we are continuing on with some material, the new chapter. So let's see, let's get this started. So we're rolling, etc., etc. Now, let's see. So whenever you're happening to watching this, good afternoon, good morning, good whenever it is. Hopefully you'll enjoy this as much as, or hopefully you'll find this as informative as when we have class. Sorry I couldn't be available for an in-person lecture for this Thursday. I was attending I will be attending the Steel Bridge competition, the faculty sponsor for our UG Tyler Steel Bridge team. So I'll be there in El Paso for the competition. All right, so this lecture is going to be part one of a. There'll be two videos, a part one and a part two of this chapter, for this lecture, and this chapter, which is chapter 13 in the Beer Vector Mechanics book, will be covered in two lectures, lecture number 6 and lecture number 7. Lecture number 7 will occur on the following Tuesday. Lecture 6 will be the one we're recording right now. All right, so without further ado, let us begin. So, chapter 13 here is all about impulse, momentum, and conservation of energy. So, in particular, conservation of energy. So, or if I were to phrase it more broadly or simply, what we really want to look at today is energy and momentum methods. Energy and momentum methods. So you may have seen this before, you may remember this from earlier classes, especially high school level physics and things like this. But in this they'll obviously, like a lot of the things we've seen, you have seen some hints of this before, but on a much simpler level. And also in your university physics class as well. Now, in chapter 13, we're going to still restrict ourselves to working with particles. So still working with particles, we're not dealing with anything that can rotate yet. We'll get to that later. So still working with particles. Now, you may be, so energy methods are obviously something new, but at first you may be surprised, or you may be asking yourself, wait, didn't we work with momentum last chapter in the previous two lectures? And yes, we did. But there's a slight difference here. Previously, we have simply been working off of the base equation, Newton's second law. Previously, we have worked from Newton's second law. Directly from Newton's second law. Second law, which of course is the summation of forces is equal to mass times acceleration. So you would look at a system, look at the forces on it in the x and y direction, give ourselves some inertial vectors x and y, and from that we would describe the behavior of the system. In this chapter, we're going to be working with something a little different. We're going to be instead of working with this, we're going to be working with something built off of this. In this chapter, we deal directly with the conservation of momentum and energy. Of momentum and energy. So we're actually going to say, instead of doing a very detailed force balance on the system, we will instead be looking at more fundamental laws of conservation of momentum, etc., etc. Okay, so let us break this down a bit more. So let's see here. as we mentioned before, as I mentioned, let's look at this a bit more. So let us break this down. I want to create a little chart showing some of the approaches we can take to kinematics problems. Approaches to kinematics problems. Approaches to kinematics problems. And I'm going to sort of lay 3 of them out. And this is something you might want to write down, or that you should write down definitely, to sort of guide your study as you go through this course. Maybe definitely help prepare for may definitely help to prepare for the first exam. Okay, so the first one we could go and say, okay, let's start with the forces and accelerations. We could use a forces and accelerations approach. Forces and accelerations. And then we could apply Newton's second law. And that would simply be the sum of forces vector equals mass times the acceleration vector. I didn't write the vector last slide, but I was being a little careless there. Okay, so that would be one approach. What else do we got? So let me put this in its own little box here. I could also use velocities and displacements. Velocities and displacements. So I could use a velocities and displacements approach. I could analyze something according to velocities and displacements. And then we could go down, and our tool of analysis would be work energy. And we will learn about this further on the next slide even. But what's special about work energy really is that it's path and time independent. So I could say T1 plus U1 to 2 equals T2. And what this would mean is the total energy at point 1 plus any work done on the object or change in the internal energy from point 1 to point 2 will equal the total energy 2. And we will explore that later on. So it's a work energy approach, very similar to what you've seen in your previous physics courses. Again, all of this stuff comes from basic physics, dynamics, just like in statics. You've seen most of that stuff before at some level, but we're simply taking the things that you've learned at a basic level in your physics classes, your either high school and then even later your university physics classes, and expanding onto them at a greater level. So then I could also look at things in terms of velocity and time. So here time is not a factor, but here it would be velocities and time. And we could use this then if we had this. If we wanted to analyze the system this way, we could use impulse momentum. And we'll be getting into this later. Impulse momentum. So this would simply be m, and our guiding equation here would be v1 vector plus the integral from t1 to t2, of f dt is equal to m v2. This may look familiar from your physics courses. Basically, the initial momentum is equal to the final momentum unless there are any forces applied, and it is the integral of the force across the two time values. Okay, so let's get into work. In this course, we will use the variable u for work. Okay. So, let's see here. Now, first of all, it'll be important to mention that the differential variable r is our displacement. So if you remember from basic physics courses, when we look at work and momentum, or sorry, work and energy, I want to be very precise in my language. I don't want to say work and momentum. When we look at work and energy methods, we're not talking, we don't really care about the path, except in the cases of integrating forces and such. Anyway, but let's see. So differential vector dr is the displacement vector, or is the particle displacement. Differential vector dr is the particle displacement. So consider a particle, and I will draw a picture, don't worry, is the particle displacement. So consider this. Let me draw a little diagram here. And I'm going to have an origin over here. And then I'm going to have, let's say, a particle, and I'll draw it maybe in green. And this particle, I'll show it going in a straight line because we're looking at a tiny little differential element. So on this piece, on this little piece of its path, we can consider it a straight line. And this is going to be point A, and this will be point A prime. Initial and final. Then we will have an initial vector from the origin of r, and a final vector from the origin of r prime. Basically, these are two, or sorry, not r prime. This will be, let me back up a bit. The original vector will be r. The displacement from A to A prime will be dr. Just trying to be consistent with what I have up here. Will be dr. Will be dr. And the final here will be r plus dr. R plus dr. And then I'm going to have a certain force causing this change, or a present during this change. Doesn't necessarily need to be what's causing the change. Anyway, or it's causing the displacement. So let's just say I have a force vector F here, and let's say that that the angle between dr and F would be simply alpha. Would simply be alpha. So let's look here. What am I going to define work as? Well, I want to define work. And what is the definition of work in this context? Now, of course, in high school, you learn that work equals force times distance, but even then you learn that that's a very simplistic determination of it, or a very simplistic way of stating that. Even in high school, you learn that you need to take the component of work along the displacement vector. So we can't just say F times dr. We have to say du. Let me actually write this out a bit first, though. Work of the force F. It's not going to be simply F times dr. It's going to be du. And again, I'm using capital U for my work. And notice there should be no vector on this one, because work, if you remember, is not a vector. It is a scalar quantity. And this is going to be equal to F dot dr. And this makes sense if you think about it. All dot products should be scalars. So we're going to take, dr is going to be vector, force is going to be vector, and when you take the dot product of both of those, you get a scalar. And so we're basically looking for the component of F along, basically what we're trying to find is, we're finding the component of F along dr and then multiplying the two together is another way of conceptualizing it. And then another way to describe this would be to say here, well, if I also wanted to consider this arc length, I could say this is F ds times cosine of alpha. If I was looking at more a arc length approach, times the cosine of alpha, or perhaps a simpler way to express this would be I could also look at this at a component approach, and perhaps this would be the easiest. And don't worry, we will work through some examples here. As always, I like to work through the theory first and then move on to some specific numerical examples. Fx dx plus Fy dy plus Fz dz. And again, just to state, work is a scalar quantity. Scalar quantity. It has only magnitude, no direction. No direction. Kind of like my lectures sometimes. And of course, dimensions, the dimensions for work. Well, we know that work is, or has units of force times distance. And so work equals force times length, or everything in terms of distance instead of, everything in terms of length instead of distance. It is length times force. So in terms of the fundamental the fundamental dimension systems that we discussed earlier, it would be a quantity that would be something like F times L, if we were using a force as a fundamental quantity system. Or if I were going to use an MLT system, it would be something like, let's see, mass. There would be an M here, and then times meter per second squared, for example. So we would have a length, a times the -2, and then all of this times another length for the actual length. So, but we don't usually need to worry about such things. And of course, if you are having trouble to remember, if you're having trouble, did I really just say if you're having trouble remember? Great. Anyway, 1 joule is, of course, our standard metric unit for work is going to be the joule, and 1 joule is going to be equal to 1 Newton times 1 meter. And then we can also have we also want to be able to use English units here. That is one difference between your standard university physics and an engineering course. Typically, we also teach you English units in the engineering courses. So 1 foot-pound. Well, again, we can take the unit for distance and multiply by the unit of force and get 1 foot-pound, or approximately 1.356 joules. So we will be using the unit foot-pounds for energy if we're going to be using a English system of units. Okay. So let's move along here. Let us discuss the work of a force. All right, let's see here. How might I best explain this here? Okay. So again, work is a force during a finite displacement, and let's look at this here. I want to draw out a diagram that's a bit more involved than I normally draw. What I normally draw out, I should say. Let's see. Okay. Yeah, that makes sense. Okay. So let me draw a little more complicated. I'm not the best artist, you know this, so I'm going to try to draw this of reasonable quality. And I could just plop in diagrams into these PowerPoints, but I really don't like doing that. I think it detracts something if I just copy and paste something in here. So consider something like here. Say I start at the origin. Say I have an object that starts at the origin. And perhaps it's going on a certain path. Maybe let's say a circular path. And then let us say that we have okay, so it's on a certain path with a certain arc length. And maybe it's not starting at the origin, but let's say we have something like this. This is the path. And let us compare 2 points. Points A1, 2 points in space, A1 and A2. Now, there would be different paths. So I want to distinguish between R and S. S would be the actual path of the particle. It would be the actual distance traveled. R is simply displacement. It's just in a straight line distance, final position minus initial position. S, again, is our actual path length, our actual arc length. So this would be something like S1. I would call this one S1. And then in case it's not very clear, I'm trying to draw these as curved arc lengths. And this would be S2. S2 here. And then, let's see here. If I were to draw out some paths of integration, at some point we would be looking at we're going to be looking at an integration between A1 and A2, and I would have a little element A here. And here I would have a dr, which would be my little displacement vector, dr, and ds would be the little arc length integration, my little element of arc length integration, ds. And then as this thing is moving from A1 to A2, there may also be a force, and I will call that force F. Let's do something like this, F at that location, and then there would be an alpha between the path and the object, and the force. So maybe that's an alpha here. And then at any given instant, my actual arc length is S. So I know this is a little messy, but hopefully you can kind of get the feel for this. This is, let me label this as A here. So basically what I'm doing is I'm taking my object, at any given, at my integration point, I'm saying there's an object at point A. And we're going to take this element of integration, this tiny area from A1, or for this tiny piece from A1 all the way to A2. And at any given place, it's going to have a coordinate S, or an arc position S, an arc length S. And there may be there's going to be a certain alpha between the force and the path of that location. The dr is going to be the tangential vector from the arc length, and then S is going to be the actual arc length. Okay, and again, once I work through the theory, I think this can seem more complicated than it needs to be. So I know seeing lots of integrals can be scary at times, but don't worry, we'll see some actual worked out examples here. Okay, so if I were to work through this, I would say, if I wanted to develop this, I could say that the work of a force during a finite displacement during a finite displacement let's say I want to look at the force of the work of a force during a finite displacement. So we're looking at the u from 1 to 2. Well, this would be the integral from A1 to A2 of f dot dr. And then this would be equal to the integral, or from S1 to S2, of f cosine alpha, s cosine alpha ds. If I change this from a dr to a ds, or simply the integral from S1 to S2 of ft, where f is the tangential force. F tangential. So f sub t would be tangential force. Ft ds. Or I could say it is the integral from A1 to A2. The integral from A1 to A2 of f of x dx plus fy dy plus fz dz. And then that actually might be the most convenient one to work with, depending on what kind of problem we have. Or another way to think of this is that work, so let me do this here. Another way to think of this is that work can be thought of as the integral or the area under. Okay, so let me show you this. Work can be represented, or just let me say is represented as the area under the curve of ft plotted against S. So, in other words, if I had a certain object path, so let me show, on this axis I would put S, my position, or my arc position. Ft on this axis, the tangential component of the force. In other words, I would want the force, only the force that is basically F cosine alpha. I want the component of F that is along the path of the object as it goes along. So say we had something like this, and it can be as complicated as you want, but say you had something like this. I'll just draw a potato curve, just a random curve kind of thing. Something like this here. And if I was looking at this from S1 to S2, and if you're asking where that curve came from, this doesn't directly correspond to the previous one. I'm just showing a curvy line to indicate that it can be arbitrarily complex. So this could be S1, the initial position, and the final position. And the area of this would be equal to our work. The area under this curve, because again, integrals mean area. Well, they don't mean area, but a graphical interpretation of integration is finding the area under curves. So this would be our area, or simply our work. U, or U from T1, or U from 1 to 2. All right, so, and of course, just to state it again in case it wasn't clear, Ft is the force in the direction of displacement ds. Of displacement ds. All right. Okay. So let's look more at this. So let us look at a particular example of work done by a force. So let's look at the work of a force, or a particular example of it, perhaps the simplest example. Work of a force. Let's see. So let us look at an example of the work done by gravity. So I like to use purple, and for some reason in this class I've settled on using purple for object paths. So I think I'm going to try to stick with that. So let's say I have a path, an object going on a path, and it starts at location 1, A1. It's going to start at location 1, and then it's going to end up at location 2, and then somewhere along the line, it's going to, actually let me show this as maybe on top of here. I might like that a little better. So basically I have a hill here, for example, and then we have a box or something that's going up the hill. It starts off at A1, ends up at A2, And then at some point along the middle, it's just at a given a value. And so let me look at some, and then I have, let's say I have a level ground, or my datum line. This is a term you hear a lot in energy balance problems, datum. If you hear the word datum, what that means is datum refers to the zero point. Just like when we get to gravitational potential energy, we'll see that gravitational potential energy must always be defined relative to a zero line. If I'm in a room on a second floor, for instance, and if I ask, what's my gravitational potential energy? Well, it depends on your perspective. If you ask, someone on the same floor as I am, they'll tell you it's basically zero, maybe plus or minus a few inches for relative height differences or something. If you ask someone standing on the ground floor or outside the building, you'll get a different value, etc., just based on the relative height differences that we're looking at. So, and then corresponding to this, we would have some heights. So let's say here it's at y1. Here it's just at a given y value. And here it's at y2. And here it is at y2. And then I could look at the work. I would want to find the work of a force, or of the force of gravity. So let's say I wanted to find the work of the force of gravity. Now, obviously, this thing would not move up the hill by gravity. I don't need to tell you that. You should be, if you can't figure that out, well, we're gonna have problems. But I don't think that's gonna be an issue. So there would obviously be some other unshown force doing this, but we can actually look even at the work done by gravity. So let's say we would have a weight here pointing down, and then let's say some little location further up. Maybe I'll draw I'm drawing this as a sort of dotted line. This would be perhaps a dy. Our change in height for a little element of integration. So a dy. And then let's say we want to look at the work done by the force of gravity again. Well, it's going to be, we saw this earlier, that du, again scalar, is f of x dx plus f of y dy plus f of z, or fz dz. Now, look at what happens here. This is something really cool. So fx dx plus fy dy plus fz dz. Looking at this here, do you see any forces in the x direction? If I define x as this way, do you see any forces in the x direction? I don't. So that thing, because this is going to be 0, this whole term goes away. And then same thing with the z. Z would be into or out of the page here, so that's going to go away. We don't have any z forces. So all we are left with is an f of y dy. And then I could also call this negative f, or simply negative w dy. Negative w dy. That's what our du is going to equal, assuming I consider w to be a positive value and then put a negative on it to make it. I do need to make sure that my dy and my weight are pointing in opposite directions, because my weight is going to be pointing downward and my dy is going to be upward. So that would be my du. And then I would get the u from 1 to 2 is equal to the integral from y1 to y2 of w dy, or negative w dy. And it might be really complicated if, say, if f was a force that was changing with respect to x or something, or respect to y. This would be a bit more complicated, and we'll see examples of that. But in this case, weight is constant. It's not going to change. Whether I put it here or here or here, it doesn't matter. So weight is going to be constant with respect to y. So I can just pull out the whole negative w. I can just say negative w integral from y1 to y2 dy, y1 to y2 dy, Or simply, this will just become y, so that will just be negative w times y2 minus y1, or I could call this negative w delta y, and that would be the work done by gravity from 1 to 2. It's a very general equation, very useful equation, but created from the basic definition of work. Negative w times delta y. Negative w times delta y. Okay, so let's back up. Let's take a look again and then reinterpret this, see what's happening, etc. Now, again, if I look at this, what is happening is negative w delta y. So there would be some sort of force that is raising this thing up. There would have to be some sort of force that is raising this thing up. And in turn, say I could model as a vertical force or whatnot. They would be a bit more complicated than a simple force pointing straight downward. But here, for the force that was whatever moving this, I would find that if I worked through the calculus, I would probably find that the work is equal to, it would be a positive value. There might be further negative work coming from the forces, the normal forces, etc. But at least here, the work done, there will be a positive work done on the object by whatever force is moving it. So let's just keep this in general terms for right now, fairly simple. There's going to be a balance of forces here, or a balance of works more precisely. There will be a positive work that is raising this block to a higher elevation, giving it further potential energy. And there will be a negative work done by gravity that's preventing that from showing up as an increase in velocity. So if, for example, if I moved this from A1 to A2 at a constant velocity, the object would be gaining additional potential energy, but it would be losing, but it wouldn't get kinetic energy. So anyway, that's how this would, the work done by gravity is what's going to balance the work done by the propelling force. So again, the work of the weight is equal to the product of weight W and the displacement delta Y. Okay. So, or another way we can look at this, so work is going to be negative if we're going from A1 to A2, but if the object were falling, if gravity were actually propelling this, the work done from A2 to A1 would actually be positive. There would be a positive work done on the object, and it would be expressed as an increase in kinetic energy. But let's keep looking at this. Or let's look at another example, I should say. Okay, so next I want to look at an example of a simple spring. Now, we remember from basic physics that the magnitude of a force exerted by a spring and we'll talk about this a lot more when we get to vibrations in the last chapter. Exerted by a spring is, of course, described by Hooke's law, is F equals negative kx, or sometimes just kx. So the magnitude of the force is F equals kx, but the actual force would be negative kx, where k, of course, is the spring constant in, say, newtons per meter or pounds per inch or something like that. Force over distance. Spring constant in newtons per meter, pounds per inch, etc. Now, let us say that we had so we need to describe what these things are. So let me draw a couple springs to sort of illustrate this or illuminate this or whatever verbiage we want to use. So I'm going to draw a couple springs, and we're not dealing with vibrations, so I won't say there's a mass at the end. Although maybe I'll draw a little block to clearly indicate their end position. So let me draw a couple springs, a couple happy springs. Here. And let's say I had a position, let's call this A0 for the initial position, and I'll describe what that means. And then A1 and A2. A1 and A2. Okay, and then I will also mention that at A0, what is special about A0 is that this is the undeformed. This is the undeformed spring. So basically, if this thing was just sitting there by itself, with no displacing force, it's not vibrating back and forth, it's at rest, it's happy, etc. This is the undeformed length. That is what A0 is, the undeformed length. Then, if I strike a line downward, I can get, say, an S1 and an S2. Or actually, in this case, I'll use an X1 and an X2, because this is going to be a horizontal force, instead of just a generic path length, or path S. So this is going to be S1, and this is going to be S2, here. All right, and then we know that there will be a force exerted. Wherever the block happens to be, there will be a force. So if I were to draw this here or here, in each case there will be a force. And it looks like the displacement on this one is, let's say this is twice this one or something. That's not actually going to be reflected in my math, but actually I won't try to get them an exact value. I'll just try to show that the force here would be larger, or sorry, the force on 2 would be larger than the force on 1. So I'll draw that vector longer. F2, F1. There would be different forces at the different positions. So in the previous example with weight, or with gravity, or whatever you want to say, with weight, I guess, we didn't need to consider the force was not itself a function of displacement. But in this case, the force itself will be a function of displacement. This is something that we really do need to use an integral to solve. So here, again, work will be a function. So let's consider the work of the force exerted by the spring. So let's say I want to analyze that. Work of the spring force Well, du is going to be equal to negative f of x dx. So previously up here I didn't put the negative because I was just looking at the magnitude, so that's a key word. Magnitude, we would not have negatives, but I do need to have some sort of negative here. You see, the f of x is going to be opposite the displacement. The displacement here is, as we move this thing to the right, the force is to the left, so we absolutely do need a negative there. Negative f of x dx, or simply negative kx dx. Oh, sorry, let me just say negative f dx. Negative f dx, getting ahead of myself, and then negative kx dx. Then if I simply integrated this, I could integrate both sides, and I would get that the u, the work from 1 to 2, is equal to the negative integral from x1 to x2, of kx dx. And I could then pull out the k, and this would then come to 1/2, or I could simply say 1/2 k times, well, it would result in a 1/2, but I could pull out the k, etc., etc., and I would get a result of 1/2 k times x1 squared minus x2 squared times, again, x1 squared minus x2 squared here. And the reason these are flipped normally is because the reason that the negative disappeared is because these flipped around. Normally we'd have upper bound minus lower bound, but when I move the negative in there. Oh, derp. That shouldn't be there. That should be there. Much better. Okay, let's see. Now, let's say I want to plot this out. Let's do just like we did with gravity, or just like we've looked with simpler functions, let us look at a force displacement diagram. So x and force here. Well, let's say I have this. It would be a simple linear equation where f equals kx. F equals kx. And I would have 2 points, 1 and 2. So let's say I have x1 and x2. And of course we would be trying to find the area under this curve, because that would be our work. This would be our work. And we would have f1 and f2. We would have here, I don't want to use red again, that would be bad. I already used that color, so let me use aqua or something. Our f1 value and our f2, so colorful, very festive. And of course, let's say the distance between these is delta x. Delta x. Okay, so the reason I drew this out is I wanted to relate a few, I wanted to sort of get a few implications or interpretations of this. So just a few notes. Work of the force, for the spring force anyway. Oh, I got ahead of myself. The work exerted by a spring is positive when x2 is less than x1. x2 is less than x1. When x2 is less than x1. Is less than x1. i.e. returning to its undeformed position. Returning to its undeformed position. So in other words, if it's pulling back from its deformed position, it's going to be accelerating, so work will be positive there. But also, so we know this, but how does that not clash with this? Well, the way we can balance this is by saying that the work of the force exerted by the spring So we know this. We know that the work exerted by the spring is positive when x2 is less than x1, I should say. x2 is less than x1. In other words, it's getting closer to the spring. We know this. As we release a spring, it's going to go accelerating towards its undeformed position. So the x2 there would be less than x1. It would be closer at the end than the beginning. So, but how do we resolve that with what we've already seen? How do we possibly resolve that? Well, we can. Exerted by work of the force exerted by the spring. So the work of the force exerted by the spring, the way we resolve this is to say that the work is that the worst, I cannot talk. The way that we resolve this is to say that the work of the force exerted by the spring is equal to the negative area under the curve. Equal to the negative area under the curve. Negative area under the curve of f plotted against x. Plotted against x. Or u1 to u2, or u1 to 2 is equal to negative 1/2 times the, this is just the formula for the area of a trapezoid, f1 plus f2 delta x. f1 plus f2 times delta x. f1, f2 delta x. Or an alternate way to do it, so we could use it like this. This is if we were working only with the magnitudes of f1 and f2. Alternately, we could look at the actual values, and we could say something like, okay, well, another maybe cleaner way to do this might actually be to use although it gets a little more confusing. If I were to put the f here and show that it's actually negative, right? Maybe a positive f and a negative f. Negative f. This is what's actually happening. If you had if we looked at it for force versus displacement, there is that negative. The force is actually going to be opposite the displacement. So it would actually, I think, look something like this. I think this might actually be a better description of it. F equals negative kx. That may be a better way to visualize it. And then you would clearly have a negative area. You'd have an x2, x1, f2, and f1. So maybe that would be another way you could look at it if you wished as well. All right, moving on. Let's keep working through it. A lot to get through in this chapter. This is going to be a rather long chapter. Have a lot to get through. All right, so let's see. And that's the same idea. So let's continue working through this. Let's work through more things with springs here. So if I had again, work of a force continued. Work of a force here. So if I had a spring, again, a knot, and here, and actually I just had the same type of system where it's, you know what, I don't think I need to draw the whole thing out, so you can reference the other back there if you just want to save a little time. So again, looking at the previous diagrams, let's say the block moved from, if the block moved, so just a further exploration, where we had, again, a naught is the undeformed length, a1 is a location to the right of it, and a2 is even further to the right of it. So if the block moved from a naught to a1, I just have a few questions here, conceptual questions. From a naught to a1, is the work positive or negative? So think about that for a second. So we're going from from a naught to a1. So this is a question, conceptual question. Is it positive or negative? Is the work positive to negative if it goes from a naught to a1? And the answer is it's negative. And the reason is because we have our delta x this way and our force this way. Our force is directly opposing our motion. And so whenever you have the force directly opposing the motion, the work has to be negative. Then another question, as the block moves backwards, say it's vibrating back and forth, as the block moves from A2 to A0, is the work positive or negative? I'll just abbreviate U plus / minus. And the answer is this one would be positive. Because, why is that? Well, as the block is moving in this case from A2 to A0 back again, in this case, the displacement is pointing in this direction, and the force is also pointing in this direction. So everything's lined up. If the force is going in the same direction as the motion, then it has to be positive. All right, so let's look at something here. Let's say I wanted to look at something with a, let's say I wanted to consider gravitational force in, say, an orbit. This would be a bit more complicated than what we were looking at previously. We looked at weight previously, but we were considering usually when we talk about weight, we're talking about objects at or near the surface of a planet, close enough to the planet's surface that we can consider that through the motion, or through the object's entire motion. So basically, let me back up. If we're saying weight of an object, if we're talking about an object's weight, usually what we're talking about is a system where the object's path is close enough to the surface for its entire path that its weight is essentially constant. But we know that gravity actually doesn't work that way. It's an inverse square law of force. So in reality, if you double the distance from a mass, you decrease if you double the distance, it's 1 over r squared. So you decrease the gravitational force by a factor of 4. Now, for a sphere like the Earth, you have to the distance we're talking about is the entire radius of the Earth, which is what, 7,000 miles, 6,000 miles, something like that. I'm probably getting that wrong. Don't quote me on that. It's late at night. I don't feel like looking up right now. But anyway, if we're talking about, again, a gravitational force, it's going to be relatively constant near the surface of the Earth. Because yes, if you go up even a kilometer or two, yes, it might be a slightly tiny fraction of 1% lighter a mile up than it is at the ground, but you're talking a fraction of the entire radius of the Earth. It's minimal. So let me look at, say, this would be something like an orbit. And I want to look at the work done by the force of gravity in an orbit. And we'll see this more in later problems when we study orbital dynamics in a bit more detail. So let me draw out let me put one of the masses, maybe the big mass m, at the origin. So here my origin. Let me draw this kind of like, okay, I'll put it down here. Maybe need a lot of room for this. This is a big drawing. And then, so I have the origin here, and I have my big mass. I'll use my big mass capital M. I won't use M1 and M2. I'll use the capital M, small m. And usually when you use this type of notation, what we're signifying with a big M is that we're talking about a system where there is a very large mass disparity between the objects. In other words, this is something like the Earth and a satellite, or the sun and a planet. In reality, we know that all objects move or affect the motions of every other one. So as the Earth, or as the moon goes around the Earth, the moon also tugs back and forth in the Earth a bit, which is what causes tides. And if you could look at it from above, you could actually see the Earth wobbling back and forth. And there actually are some cool videos, some animations that have been filmed by spacecraft of this. You can look that up if you wish. But anyway, when we say so that's something for the moon. That's an example of something like the moon. But when we're talking about something like a satellite in orbit, that is such a small nothing compared to the Earth that we can essentially treat the Earth as just stationary, sitting when in an orbit. So, but anyway, we're not as stationary, but completely unaffected by the gravitational force of the other body. So if I were to, let's say this thing is so small mass m is on a path, And again, I'm going to consider the bigger mass, which could be the Earth, it could be the Sun, whatever you want it to be. And it's on some sort of elliptical path here. And you know what? I didn't get it right. Get it right. Why? I cannot talk. It's too late at night. I did not get it quite right, but there we have it. Okay. Sorry about that. So let's say we're at point A here. And at point A, this would be at some random point in our integration. We would have F pulling the object toward the larger mass, F, and we would have negative F pulling the larger planet or moon or star or whatever it is, negative F, the opposite vector, pointing toward the smaller mass. Then, let's see, so I want to define two other points. These are my bounds of integration. Again, I want to analyze this across a path. I want to look at through a portion of the object's orbit. So I'm going to say maybe A1 here, point A1, and point A2 here. And then I would have, say, maybe something like this. Got it. R1, our position vector 1, and R2, our radial position vector 2. And I'm just going to move A2. Problem solved. Perfectly straight. These are perfectly straight lines. If you see them as curved, you're completely imagining it. Okay, and then I would have at that same time, I may have an R. So again, that would be R1. Oh, I should probably label R2. So that would be my final vector, position vector. And then at some point, at the point that we're actually integrating, I might have, let's draw a dashed line so I don't cover up the forces completely. I would have a R just at that point. And then I would have at that point at our point of integration, I would have a theta, and then here, actually, let me see this. I think I actually labeled my R wrong. Oh no, that's not good. That's a bad thing to mislabel here. Uh-oh. Okay, so, that's not good at all. Okay, these forces are going to go away temporarily. Sorry about that. That's actually a little error on my part. I meant to draw my forces as a little bit, I meant to draw my R as a little different from my forces. I still want the forces to be at that location, but I want my R to be a little bit past the forces. I want my R to be a little bit past the forces. Negative F and positive F. And so basically this thing's going to go over the path of our integration. This thing's going to go from A to A prime. From A to A prime. And there will be a, let's say here, let's say how might I express this here? Well, R's, let's say our R's are our distances. Okay. Actually, I probably could have, you know what, now I don't think of it, I probably would have been fine with that R there. Sorry about that. I'm getting all kinds of confused tonight. Let me line that up a little bit better. What I'm really trying to get at is that there may be a change in radius here. So there would be an original vector of magnitude R. And then let's say there was a change to get to A2. So maybe R now comes up a little bit short when I rotate it. And this would be, this here would be R, but then I would also need a small dr here, a small dr here. And theta, now we can explain, will go directly to here, and there would be a change in theta, a delta theta here, from a to a prime, a delta theta here. So theta is going from the axis to the original arc radius, or the original radial vector, and then the delta theta is the change in angle. So let's work through the integration. Or let's describe this here first. So what I'm trying to label here, or what I'm trying to get at, is work of a gravitational force and again, we're talking about a mass m following a fixed point. So du would be equal to negative FDR, or if I used my law of universal gravitation, negative g times m, big M, little m, over r squared dr. Or u from 1 to 2 equals the negative integral of r1 to r2 of g m over r squared gr, or sorry, r squared dr, which will come to g times m over r squared over, sorry, r2 minus g times m over r1, or simply u from 1 to 2 is equal to g m times 1 over r2 minus 1 over r1. And I kind of like that one a little better. Maybe I'll box that one. All right, continuing on here. Okay. So let's see here. Let us look at another complication of this. Let's look at something here, another conceptual question. So say I have a ramp, and I may have misquoted a little bit earlier when I mentioned normal force, and I'm getting myself in trouble. I gotta be a little more precise with my language. So here, so let's say we have a slope here, and I have a block that is going to slide down from here to here, 1 to 2 here. And the question is, does work, or does the normal force, does normal force, so block sliding down ramp, block slides down a slope, slides down a slope, from 1 to 2. So the question is, does normal force do work? As block slides from B to A, or from 1 to 2. As block slides from 1 to 2. And the answer is no. And to solve this, or to see why, we can look at a free body diagram. If I were to draw a free body diagram of this block, I would see that I have, actually we can, I'll do another question first with this, but I'll also ask a question, does gravity, or does weight do work along the same path? And the answer here is actually yes. And I can explain both of these with the same free body diagram. So let's assume this is on a frictionless slope. So I know that normal force, F sub n, is going to point upward from the slope. But gravity is going to pull straight downward. And if you remember from high school physics, you can work through the trig yourself if you'd like, or I can simply say the along slope component of weight, I just remember this from my own high school physics courses and from things through the years, this is going to be W sine of theta. Say this is at a certain angle theta. And then this would be at W cosine theta. These would be the components of weight. W cosine theta. And of course, our delta x would be, our x would be along the slope like this. Well, look here. Now when we have this, we can clearly see why each of these does or does not do work. See, normal force here is going to be perpendicular to the x direction. And even if the slope were curved, the direction would continuously change and the normal force would continuously change. But in each case, they would be mutually perpendicular to each other at all points. So if this thing is it cannot move through the ground. So at all points, the path of an object sliding across the surface must be perpendicular to the normal force. So normal force really can't do work except in some really weird situations. But gravity here, look at gravity, look at weight. It has a perpendicular and a parallel component. The perpendicular component will not do any work because it's also perpendicular to the slope, or sorry, to the path, but the parallel component, the component that is parallel to the slope, will be along the path of the object, and that will mean, or along the path of the block, and that will mean that it can, in fact, actually do work. So the question said, so I sort of raised a question there. How could normal force do work? How could normal force do work? That's an interesting one. About the only way I could see the normal force doing work is if I actually have something like this. So imagine, I really have to come up with a really contrived scenario. And at this point, it's kind of silly, but let's say I had and we could think of any scenario where this might actually occur. And what I want to do is I want to try to come up with a weird scenario where I could actually make normal force do work. And I don't want friction to do work. I don't want it to be like one surface clinging to another via friction. I literally want the normal force to do work. And one weird way I could think of this is imagine I had something in the vacuum of space, so we don't have to worry about gravity. Well, there's gravity, but it's far away and constant. And say we're talking we could talk about something in orbit, or it's between stars or something like that. So gravity basically doesn't need to appear on our free body diagram. Let's just say that. So let's say I had some weird thing like this. Let's say I had a rocket engine, and I'll just draw it as a kind of thing like that. And I'll show fire coming out of the back of it because, as we know, rocket engines are just burning all the time, right? That's how that works. Fire out the back of it. Great art skills here. Okay, so, and then let's say that attached to this, part of this rocket was a kind of thing like this. I don't know why anyone would build such a thing, but I suppose you could if you were so inclined and had a lot of money to burn. And then let us say, so there's this rocket engine here, and maybe this would be like a cutaway diagram. So there's a circular rocket engine and a circular kind of cup kind of thing here, just a collar. And then I could have another, just a block or or perhaps this is more like a hockey puck shaped thing, or just a cylinder or whatever you want it to be. And it's not physically attached. In fact, let me draw it as another color to make, and I'll draw something like this to make clear that I'm talking about a separate object. So maybe I had a separate object here. A cylinder would do nicely. And you wouldn't want such a large gap. This would actually be in direct contact. I just want to be able to show that maybe I'll do something kind of a little closer. Something kind of like this. And so these are not physically attached to each other. This thing is just sort of sitting there. It's kept in place by the collar. It can't go left or right by these arms here. But the only thing accelerating is direct bearing or normal force between this and this. Interesting. So in other words, if I were to draw out the path of the free body diagram of the rocket, so I have the rocket here. Let me try to draw a simplified form of it so I don't have to draw the whole thing again. The weird rocket gripper thing would have let's say this was moving at accelerating at a constant force, or let's say it was, I'm trying to think how this would move at a constant velocity, but it would be accelerating. Let's just ignore acceleration right now. Let's look only at the forces. I'd have to draw an inertial diagram. I don't want to do that. So it would have a F exhaust here, propelling it, and the exhaust would be being forced the other way. And then there would be a F normal pushing the sort of gripper, a normal force here. And then the block, or the cylinder, or whatever it is, the disc, whatever you want to use, would be over here, or actually be right next to each other, but I'm drawing them as separate so I can label the forces here. So let's see, let's get this. I want to get a cleaner force arrow, and then maybe have another normal force here, Fn. And if I look at the direction of displacement, what do we get? Well, the direction of displacement is, of course, this. So this is a kind of contrived scenario, and I'm sure we could come up... Actually, wait. Oh man, I'm stupid. There's a much better scenario. I'm sorry, this is the dangers of coming up with things off the top of my head. I was building a crazy rocket thing, and I just realized there's actually a much simpler example and terrestrial example of a... so this would be one weird example of normal force doing positive work on an object, but a much simpler one, in fact, would be the common elevator. I don't know why I drew this thing, but I guess that would work as well. So if you're in an elevator and the elevator is accelerating upward, it can be different than accelerating downward. If I draw your free body diagram, you would have weight doing negative work on you as you went upward. Let's say you're going at constant velocity. Let's make that nice and simple. So acceleration is 0 actually, but so I'll have to replace that A with an X. So you would have the normal force pushing up on you and the weight pushing down on you. And so weight would be doing negative work and the normal force would be doing positive work. Very simple. So I guess we don't need the crazy gripper rocket, but that's what you get for putting lectures together late at night. All right, so let's see that. Move along. So let's create a nice sort of summary of what we've seen here. Forces, let's see what kind of forces do not do work. Forces which do not do work. Forces which do not do work. So in other words, there are two ways you can get forces to not do work. You can either have ds be 0, that the change in distance be 0, or cosine alpha equals 0. This is what we've been talking about, where the force is perpendicular to displacement. So a few examples. A reaction at a frictionless pin on a rotating body, at frictionless pin supporting rotating body, at frictionless pin, this would be because there's no displacement and we're not considering rotation right now. So this would be an example of the first condition, ds being 0. There's no translation. Pin supporting rotating body. Supporting rotating body. Rotating body. Also, the reaction at a frictional surface when body in contact moves along surface. So the normal force is perpendicular to this. At frictionless surface, when body moves along surface, and let's see what else. There's some more. These are just a few examples. I could also mention the reaction at a roller moving along in its track. On a roller moving along in its track. That's just basically another example of frictionless things moving along in its track, because it will have a vertical force, but it's going to be perpendicular to its displacement in its track. If you can't visualize that, imagine I had a roller in a track like this, like a long slot, like this. And it cannot support a force left or right because it will just flow. But it can resist a reaction up and down here, perpendicular to the slot. So, but if we say, especially if it's frictionless here, we'll say that it can exert a force here, but not this way or this way. And of course, we have mentioned that the weight of a body will do work, but there is one case where it won't. Weight of a body, and this is just the direction type of thing, the cosine alpha equals 0. Work of a body when its center of gravity moves horizontally. Its center of mass, just say center of mass, moves horizontally. Because this would be the case if you have a weight or an object moving horizontally, gravity will be, if it's moving perfectly horizontally, the gravitational force will be perpendicular to that motion. So therefore, it cannot generate any work or perform any work. Here, all right, so let's continue. Look at another principle here. What is this? Yeah, these videos are going to be a bit longer than I would have hoped, but this chapter is a long one. Probably should have split this into 3 lectures, but maybe when next time I teach that, I'll do this chapter over 3 lectures. Anyway, so let's see. You know what? I think I'm going to take a quick break and come back for part 2 of this. This might be a 3-parter. All right, and thank you.